protein, or over the secondary structural elements, but you're not interested in the RMSDs over the loops. You can pass it this information and tell it that it's output an RMSD column in your score file and in your summit file that tell you this is the RMSD, the C alpha RMSD overall, and this is the C alpha RMSD to these particular sections that you specify. So I often do that with, for example, membrane proteins when I'm only interested in the RMSD to the transmembrane segments. And then your output specifications, which are essentially the same for everyone. The instruct, I have one here, and that is for the sake of time here in the workshop. But really, you want this number to be as high as possible because you want to assemble as much space as possible. Even 1,000 is not really enough. I would suggest at least 10,000. That's also a really small number. When I'm doing a production run, for example, for publication, I will fold at least 500,000 models. And that's before refinement. So I'll fold like 500,000 models, and then I'll filter them out, and then take them to atomic detail. It is really, really important, especially in the case of complicated proteins like GPCRs or something, to sample as much conformational space as possible. And you're not going to do that with 1 or 10 or 100. You really need like tens of thousands, hundreds of thousands, millions if you have the computing power. But it's still in the end much faster than MD. Let's see what else. Outfile silent.
Excuse me.
Yeah.
Can you run, for example, 10, 100 structure instead 1,000 different runs?
Yeah. So when I say
I mean, this will give different results than the one run.
Yes. Yeah. So what I would say is if you're running on a cluster, you would set up different 100 jobs with 100 instructs each, and that will essentially give you 10,000 models that are all different from each other. Is that your question?
Yeah.
Okay. So just make sure that the constant C that you specify, this flag, run JRAN, and then you give it a C number. Just make sure that C number is different for everything. And usually people write a script to make sure that C number is different for every run that you start. And that will guarantee that each folding run that you do is different from the one before.
So each run is not related with the previous run, right?
Exactly. It's all independent.
But if you don't specify the seed number, it will consider all of them as equal?
Right, because then it has a default seed number, which is this 1111111, and it will always default to that unless you tell it differently. So if you don't specify that, then it will always be the same. That's in my experience.
So the default seed is timestamped. So often when you're running clusters, you hit submit, and they all submit at the same exact time. And so they all have the same timestamp, so they all have the same seed. And so the way to fix this is whenever you're running on a cluster, you do the -JRAN and give it a different random seed. Otherwise, it will, if you're running on a cluster, it will put it specific to that time. And so what you want is, so it doesn't default to the 11111. That only defaults whenever you use the flag -constant_seed, just to clarify things.
Right. Yeah, when you're running on a cluster, they'll often start at the same time unless you get redundancy. So oftentimes what people will do is say, delay 5 seconds before I start this job or whatever, and then it will make sure it starts at a different time, and then that way each one will be independent from the other. They'll be all different, and that's how you get around. For your out files, we recommend to output the silent files, or binary silent files, and I don't remember if Stephen talked more in depth about this or not, but basically a silent file instead of a PDB file is a way of storing the internal coordinates of your structure. They take up a lot less space, so if you're generating like thousands and thousands of structures, it's much easier to put them all into a silent file and extract out only the PDBs that you're interested in looking at later. And we say binary because, again, it's just much more robust than storing just as the internal coordinates. When you're extracting the PDBs, you're more likely to come out with the more consistently come out with the PDB that you thought you were going to get. And then to run, you would just call Rosetta bin and then ab initio relax dot, for example, in my case, Mac OS GCC release. And then you have this @ sign in the flags or the options file, and then pass it your database. And then I'll often output to a log file when I'm testing, so that I can see and make sure that everything's working right. Actually, what I would recommend for setting up a folding run is do all this and then do an instruct of like 5 to make sure everything's working smoothly, and kind of time it to see how long how long it takes to generate like one model. Make sure that all your options that you put in are working properly, things like that. And then once that's working, I would do a larger number of instructs.
Stephanie, say if I want to run 100,000 on a cluster, can you just put in number of structure 100,000, and this would kind of assign to different CPUs that is available in the cluster, or this job is going to submit to one single CPU?
In the case of ab initio relax, it would only go to one CPU. It's not parallelizable. Other protocols are parallelizable.
So ab initio doesn't have an MPI?
Right, exactly. So you would have to submit like, 100 jobs of like 1,000 structures each or something like that. And this is kind of a pain, but in the next release, hopefully, there'll be a way for you to de novo fold with MPI. Right now, it's not possible.
And when I generate those 100,000 files in the same folder, they can recognize so if there one number is one structure already existed, so it knows that number one is already generated, then it will go to number two.
Actually, I think they tend to override each other unless you tell it otherwise. So, for example, in this out file silent, where is it? Out file silent here. I would say like out file and then silent, and then I give it like silent _01 dot out, silent _02 dot out. And I often actually specify these over the command line because it's different for every job that you start. And usually people use scripts to do this sort of thing, since you're usually giving hundreds of jobs at a time, or we are. So if you have questions about that further, just ask any of the people who are running the workshop. We all have experience submitting to clusters, so you can talk to us if you're having trouble with that. I don't think I need to show this to you again. This video is just to show you what is going on with when you're actually doing de novo folding. And then what do you do with your models after you say you fold 100,000 models? What do you do then? Well, like how do you assess if they're the right model? And Stephen went over this a little bit. You can determine the Rosetta energy and sort them by score, for example, and take the top N scoring models. These would, in theory, be your most energetically favorable models. This is not necessarily true. In fact, most of the time in my experience, it's not true. So I would, if I had any kind of experimental information that I could use to inform the validation of my models, that would really be great. If you don't have a native structure that you're comparing to, or maybe like a protein of really close homology, then the score versus RMSD plot is not as helpful. You could do clustering, but what you can do is pretend that your lowest scoring model is the native, just to see what the correlation with the energy function is. And so here's an example of that. I actually pretended that my lowest scoring model was the most native-like, and I computed the RMSD of all the other models to this one. This is just folding 1,000 models into for lysozyme, and as you can see, it's really, really sparse. If you really want to cover as much of the space as possible. But you can see that most of the models that I generated kind of cluster in this area, but you also get different kinds of models out here and down here. And the more you sample, the more you'll get models that are more down here. And this is just to show, like, when I'm benchmarking, I will compare them to the relaxed native structure of T4 lysozyme. So I took the T4 lysozyme structure, relaxed it in Rosetta to get the energy of it in the Rosetta scoring function. And as you can see, Rosetta scores the native structure much lower than the models that it's generating, which shows us that the scoring function is robust. And then you can see that some of these models actually get relatively close to the native. This is a C alpha RMSD over all the atoms, over all the whole sequence. But again, if you sample more, you're more likely to get models that are more like this. Then you also get a lot out here, but you're also more likely to get some down here too. And those are the ones that you're interested in. And in this case, I took the top 5 scoring models out of this fold of instructs of 1,000. What are the scoring terms in Rosetta membrane, and things like that. So, as I said yesterday, they're essentially put together the same way as soluble proteins, except over a database of membrane proteins. And unfortunately, since we don't have many membrane protein structures to compute those statistics over, the knowledge base is quite small. And so you just have to keep that in mind when you're using Rosetta membrane. But essentially you do the same thing. You make fragments and give it secondary structure information. You have to give it the membrane spanning information of your protein. And the Rosetta membrane actually uses kind of like I want to say implicit membrane, where it divides up the membrane into sections of like hydrophobic transitions and like water, as you can see here. And this is from the multi-pass membrane protein structure prediction paper by Yaravoy et al., I think. So you can read that paper for more information. So you may already know this. For running in Rosetta membrane, you'll need again, your FASTA file. You also need a span file, which just defines what your transmembrane spanning regions are. They recommend using the octoconservative for this. You can use whatever you want, as long as it's in the correct format. So if you already know, for example, what your spanning regions would be, then you can put that in. Sometimes we do that as a test. And you also can put in this lipophilicity file, and this helps Rosetta orient the helices relative to each other, so that the correct residues are facing the lipids versus facing the core of the protein, things like that. But you'll need to have BLAST installed in order to do that. We're not actually doing that today, but this LIPS file is provided for you. And then, again, you'll have to generate your fragments. They recommend only using SAM. I personally will do secondary structure prediction with several methods and take the consensus essentially. Or I don't trust just using SAM only, because I think it's better to get as much information as possible, and every secondary structure prediction method is different. So it's best just to see how they all agree with each other. And but if you want to just use SAM, you can. This is the input format. This is also in your tutorials directory, so this is also in your tutorials directory. But notice the different format of the options file. So again, you can do any one of these, but just be consistent in your file. Let's see. So yeah, this is what I was saying, the input files that you provide. And then these are the scoring terms that are different. So So first you want to tell it to use ab initio membrane protocol, and you want to turn on the membrane penalty.